Okay, good morning. Welcome back to class. Uh, we're going to talk about gravity today. So one logistical issue we should talk a little bit about, or I want to make an announcement about, and I'll remind folks too. So I posted a quiz in the homework system for uh, on Newton's laws, and I tried to design this one to be a little better in terms that there are more questions and more for the same amount of time. So there's more basically conceptual questions. So I think this will help with the problem that the quiz sort of um, the all or none nature of the online thing makes it so that if you get something wrong, then it really dings you. But if you have more questions, then I'm hopeful that it'll be kind of a little more reflective of how much people know. In addition to that, there's also one problem that's posted on Blackboard. Now, it seems that there's not a good way to do that with a time limit, so you basically don't have a time limit for that. But you need to get it in by, both of these things are posted to be due by Wednesday. So you have a few days, Wednesday evening, you have a few days to work on them and get them in. Um, yeah, my thinking is basically that there aren't great ways to do assessment online, so I don't want you guys to be stressed out about assessments. So uh, we're gonna do this and see how it goes, and we'll adapt from there. But put it to you this way: I want these systems to kind of err in your favor. So I don't want people to be stressed out about like time limits and stuff like that. So I'm trying to structure it in a way where it goes in your direction, if that makes sense. Um, but we still need to do them, right? We got to get them in. So I'll remind people and send out an email and etc. But those are live now, so you can start doing those. Um, are there any questions or concerns about that issue? So I'll put a. Let me add to our whiteboard here. I'll put a note about that. Come on, computer. Okay, so remember the rationale for this was that uh, the online system, it doesn't. Oh man, my penmanship is just terrible here. Let me try this again. So the online system doesn't let me see your work, right? Which is kind of a serious disadvantage. So we're going to also try in conjunction with this um, one problem in Blackboard. Okay. Um, and then of course we have our normal homework situation as well, but that's not due until Thursday, and that's on gravity, and we haven't even talked about that. We're going to be working on that this week. So I'll send out a reminder about this to your email as well, but I wanted to make sure and mention it in class. So are there any questions about that? Yeah, corrections. If you haven't done that and you want to do that, do the corrections as well. Yep, yep. That quiz was really short though, so I mean that's you can basically do the corrections until many of those questions were basically like multiple choice questions and stuff, so you can kind of figure them out. But if that's, yep, do that, and I'll add those scores together and give you an average. That said, with this problem in Blackboard, we'll see how this goes. This is not like I'm not convinced that this is a great way to do things, but I want you to have options, and I want us to try different things, and then we'll just go with what works the best. Other questions? Okay, well, let's talk about gravity. If you have other questions, shoot me an email, contact me in Teams. We'll get it figured out. Like I said, I mean, uh, the whole rationale for this is I want it to be in your favor, but you can kind of think about this going forward, right? You could do your assessments and stuff. You can, you have a lot of resources at your disposal that you wouldn't normally have. But I would caution you, um, you know, in the future, in physics 2021 or whatever, you're not going to probably have those resources in front of you. So I think is good to push yourself in these quizzes. You can use your book and use your notes and stuff like that, but uh, don't use the internet to try and find solutions for stuff, because I think that may really backfire. Because in the future you don't have that resource, and you're going to want to build up those muscles, those problem-solving muscles. Um, and so I would just be really cautious about that. So I think I put a note in the quiz itself to, don't use the internet or whatever. But it's really on you. So anyway, gravity. Gravity is a cool topic. This is cool. It's a real juicy physics topic, and something that you're not going to get in other courses, I suspect. Some of the things that we did in the last chapter, like Newton's laws and find the tensions in the cables and whatnot. Many of you are mechanical engineers. Those are topics that you'll see in things like statics. You're going to see that later. Gravity, I suspect you will not. So it's cool that we get to talk about this. All right, so gravity. Now let me change back to black here. So this is chapter 6. By way of contrast, one of the ways, everything that we've talked about so far has been things that are in contact. With respect to, forces and stuff. For example, you have these problems like there's a block and it's touching another block, and you push on this one, and what happens? And those forces between them are because those objects are touching. Or, questions like you have, a block and there's a pulley and this and that, and there's this direct connection, there's this cord. The objects are connected together. Gravity is interesting because it is not like that. Right? The force of gravity between the moon and the Earth, there is no touching. There's no connection in that way. It's a non-contact force, so this is different. And let me give you the definition for gravity. I'll paste it in here so you don't have to look at my terrible penmanship. So, the law of universal gravitation. And we should say this is thanks to Newton as well. I'm sure it was originally phrased a little bit differently by him, but this is the way that it's phrased in your textbook. So every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. And this force acts along a line joining the particles. Okay, so a couple important things. We're talking about force, so that's familiar. We've been talking about force in Chapter 5, Newton's laws. It depends on mass. It's proportional to masses and inversely proportional to the distance between them. So this inversely proportional bit, sometimes this is called an inverse square law for that reason, this inversely proportional to the square. And I should say that this yeah, so random question about the clipboard. Apparently Windows 10 lets you store multiple things in the clipboard, which is kind of handy for this purpose. If you want to do that, you click on the Windows key instead of Control V. It's Windows V. Anyway, but this inverse square law, you will see this in other contexts. This is not just gravity. So in 2021, or in the next, in PH 2011, you'll talk about electrostatics. Charges, electric fields, etc. That is the exact same math as this that we're talking about with regards to gravity. So you will see this exact same kind of thing with regards to electrostatics. So that's part of why it's really good for us to study this now. So then when you encounter that in the future, you kind of have some familiarity with how to analyze the problems that behave in this way. So let's put this in mathematical terms. It's a lot more concise and I think more illuminating. So thus far, we're just talking about the size of this force. So let me just describe it this way. I'll put some bars around it to say, hey, the magnitude of the force of gravity, it's proportional to the product of the masses. So actually, let me give you a picture here. Suppose you have a couple masses. Sorry. The force of gravity between them is proportional to the product of the masses, inversely proportional to the distance between them, the square of that distance, actually. And the force acts along a line joining the particles. So the force is going to act along a line that's joining them. And we know this is an attractive force, so I'm drawing the arrows pointing in. And we know also that, along that line towards the other mass, we also know that according to Newton's third law, the force of gravity on the one object will be equal and opposite in magnitude, equal in magnitude and opposite in direction to the force on the other mass. So this tells us the size. The one thing that we have not included in this definition is the proportionality constant. There is a constant here, big G. Okay? This big G, so let me just call it, we'll just call it big G, how about? Is the gravitational constant. Not to be confused with little g. which is the acceleration due to gravity at the surface of the Earth. Ah. And we'll talk about how those are related in a second. Yeah, so joining them, it's like tension. You can think of it exactly like that. It's as if there's this invisible, um, cord or something that's pulling them towards each other. Um, so we can look a couple kind of details about this. One thing is that you can see kind of immediately the functional dependence of this. So since it's proportional to the mass, if the mass increases by a factor of 2, say, then the force of gravity would increase by a factor of 2. Um, whereas since it's inversely proportional to the radius or the distance between them squared, if that distance was to increase by a factor of 2, the force of gravity would decrease, since it's in the denominator, by a factor of 1/4. Or it would be multiplied by a factor of 1/4. So it's both getting smaller as the distance increases, as well as getting smaller by the distance squared. So twice the distance means 4 times smaller force. Okay. Another piece of information, it's a little bit out of context because we haven't talked about other forces, but gravity is unique in that big G, as opposed to electrostatics, which we'll talk about later. But this big G is extremely weak. So G is very, very weak. Okay, it may not seem like it, but because we experience the force of gravity all the time, but uh, gravity is super weak compared to the other forces. In fact, this number G is a constant, and it's 6.67 times 10 to the minus 11. And the units for this are newtons meters squared per kilogram squared. And you can see that this kind of makes sense because we want this to give us a force. So we would do G, and remember it's times a factor of mass times a factor of mass over a factor of distance squared. And you can see that'll cancel, and we would be left with just newtons. So that's why G has the units that it has. So that when we use this constant, we get out a force. Okay. One other little piece of information that I'll offer as a qualitative point is, it's kind of interesting, but so we're going to talk a lot about things like planets, right? My really poor drawing of a planet or something. And it so happens that spherical, mass distributions behave mathematically as if they were points with all the mass at the center. And this may not be an obvious, I don't think it's an obvious point or realization. So um, it turns out you can prove this to yourself using calculus. Now, I know everybody is not on the same page with their calculus, so it's kind of complicated. It's not complicated conceptually, but what you end up doing is you would integrate over the density. So imagine you have like some planet or something, and you want to find what the force of gravity due to it is over here. You would have to integrate the mass contributions over the whole, the whole volume of the planet, and put that into, find the distance from each of those little mass contributions um, to your point of interest, and then integrate over the volume of the planet. And when you do that, what you find is it's as if that planet looks like a point with all the mass at that point. Okay? So you can actually look at this. It's in your textbook. They go through the derivation, but since it's a, it's a 3D integration, it's a little bit involved. But if you're curious, see Appendix D in your book. It's in the book. They go through it in all the, all the gory details. So we're not going to go through it because it would take too long for us to talk about it in class. And I don't think it would be kind of confusing, I think, for folks who haven't done a lot of integration at this point. But if you're curious, you can check it out in Appendix D. Okay. Um, Questions so far? Have you guys seen this before? I mean, just this discussion about GMM over R squared, basically. Some no's. What about other folks? Sounds familiar. Yeah, it's totally okay if you haven't seen this before. So it sounds like we have a pretty even mix. Um, okay, that's totally cool. So I'll tell you, this formulation of just finding the magnitude of the force of gravity, GMM over R squared, will allow us to solve many, many problems. I'm going to introduce it to you in a little more correct and complicated way, and we'll do some explorations in lab too that are a little more complicated. But I'll try and structure it so for folks who don't have that, who don't have as much exposure, you can investigate it, and then for folks who do have more exposure, we can go into a little more detail. So this basically what we've talked about so far is the first section of chapter 6. And the next section, it talks about the more correct vector picture of this. So I want to make a little bit more detailed diagram and put in our vectors. And then we will expand on this a little bit in lab. So just like I talked about or introduced it, suppose we have a couple masses. They're going to be connected by a vector, where this is the vector from mass 2 to mass 1. And what we're doing here is we're fleshing this out and including both the distance, how far apart they are, but also the direction information. So if we want to talk about how this force is in a direction on a line between them, we can describe that with the unit vector. So this is the whole vector that points between the two masses. The unit vector R21 hat would be a vector of length 1 that points in that same direction. So if you want, you can think about this as being basically R21, the vector. Let me here, I'll put it down here. So in other words, R21 hat is R21 divided by its length. So when you do that, you end up with a vector that points in the same direction as R21, but has a length of 1. And this is a unit vector, and it's analogous, it's exactly the same thing to what we've talked about with I hat, J hat, K hat, except instead of pointing along X, Y, or Z, it's pointing along the line that connects these together. Okay? So, if we want to be a little more precise and describe the force of gravity, 1, 2, what we're actually talking about is the force on 1 due to 2, okay? And like we described above, it'll depend, it's proportional to the masses. It's inversely proportional to the distance between them. It's going to point along that direction, which we've described with this unit vector, R21. And then the one detail is that this force is attractive. So it's going to be negative. And in terms of our picture, what that means is that the force on 1 due to 2 points in that direction. So if we're talking about the R21 direction, that is the negative R21 direction. Okay? So this is in section 6.2. And this is the more explicit, more kind of correct definition because it includes the direction information. And the reason that you might want to do that is because you don't need that information if you're just talking about the size. But if you want to see how this is oriented in space, you need to be able to put this into a coordinate system. And so we need to know the directions. Yes, this is describing M2 pulling M1 towards it. Yeah. So this is the force on 1 due to 2. So we will also talk about this kind of direction framework and implement it actually in lab. And hopefully that'll help make this a little more real. But this is the more a more complete definition. So this includes both the size and the direction. And I should say, yeah, as opposed to what we did up there, this is a vector. It's pointing in the negative R21 direction. And its size then is given by GMM over R squared. So one additional thing in this section that I think you should be aware of, and we'll look at a problem on this, probably not today, but tomorrow. And that's the fact that you can imagine, so far we've just talked about like, hey, we have M1 and M2, and we want to see what influence M2 is having on M1. Well, what if there were, more masses? What if we had an M3 and an M4 and we have an M5, etc.? It so happens that we can find the force on our M1 is going to equal the forces of these added together vectorially. And this is very similar to what we did with thinking about like chords, or imagine. Oh, whoa. Imagine a sorry. Ah, it's analogous, I should say, to if you had like chords or forces that are pulling on something, you sum the forces and then you can find the acceleration for the mass, right? We had done problems like this in chapter 5. This is the exact same thing, except the force is given by Newton's law for gravity, or this law of universal gravitation. So this is a thing we'll make use of in a problem, and probably in a homework problem as well. Um, okay. Are we back? We're back. Sorry about here. Questions? See if it reappears. Yeah, I don't know what the problem is. Sorry for the crappy stream here. Um, yeah, no, I mean my go-to is just I sure appreciate your patience with this situation. It's we're a little bit at the mercy of the internet, and as everybody knows, it can just like sometimes something doesn't work and then we're kind of out of luck. So, okay. Where we're headed with this is we've talked about uh, GMM over R squared to find the size of the force of gravity. We've found, we've described to you this more explicit and correct vector picture and what the unit vector is in this situation and where it points. And we can look at, in the next section, so a question that you probably have, or that kind of comes to mind immediately is, how does little g relate to big G? And this is, we talk about this in the next section, 6.3. And so if we were talking about, an object that's resting on a table or something, we know that the force of gravity would be mg. Well, this should be the same as of an object that's basically yeah, I know we could do Teams. The problem with Teams is there's not a good way to record. The recording stuff it's not so hot. So we had problems with this on last Monday too. It was really weird. Um, yeah, so I mean the streams are duplicate. The one at 8 a.m. is the same material. Um, yeah. So we'll be able to, I hate to have it be this way, but we'll be able to, we can refer to the recordings to kind of fill in the gaps if it's. Yeah, maybe it's an issue on Mondays in particular. I'll look into that. It seems because that's the only other time that we had issues was a week ago, Monday. And so maybe it's a case of the Mondays. I don't know. Um, but yeah, we'll definitely. I'll have everything available for you. Um, it's nice that we can interact a little bit with the stream. We could do the same via Teams, I guess, but the recording infrastructure is poor, so I've been hesitant to do it that way. Um, let's see. Yeah, the stream this morning was fine, but maybe it's something about this time of day. I don't know. Okay, so what we were talking about is just relating little g and big G, and we were just going to numerically evaluate this. So when we put in big G and the mass of the Earth and the radius of the Earth squared, we put in those numbers. Notice we have basically 6 times 6. So let's estimate this really quick. 10 to the minus 11 times 10 to the 24 is going to give us, you add the exponents, right? 10 to the 13. And then this is basically 6 times 10 to the 6 squared. So this would be 6 times 6 e to the, 6 times 6 would be add them together. So notice it's like the same thing. It's basically 36 over 36. That would cancel and give you a factor of 1 times 10. Or, not equals, but it's approximately 10. And what is little g? We know it's 9.8 meters per second squared. So it's a quick, the back of the envelope comparison agrees really well with what we know g to actually be. So that was part of why I was just, showing you the numbers there. But this is how we connect explicitly little g and big G. Yeah, so those numbers, let's see, comments. Yeah, I know a fair amount of professors are recording on Teams. I think if it worked better, well, we'll see. Maybe it will work better. I don't know. Uh, I like the mix of having stuff too, because that way, if suppose there's a problem with Teams, then we're already doing lab in there, so then we would really be in trouble. But I'll investigate this a little bit. Let's see where the numbers are from. So these numbers are just I'll just put them over here. So big G is the constant. The mass of the Earth is this 5.98 times 10 to the 24 kilograms. And then the radius of the Earth is 6.3 times 10 to the 6 meters. You'll probably want to write those on a post-it note or something, because they will appear in your homework problems and stuff. They're also in a chart in the textbook. Let me see here, I think. Or I can try and. Yeah, they're in your book as well. I don't remember the exact chart number, but 1 second. I can't find it at the moment, but these are in yeah. So let me show you a similar example problem. So we can kind of perform this same exercise, except thinking about the moon. So in other words, let's find G on the moon. Well, so what would it be? We would have, now you're on the moon or whatever. It would be the mass of your object times G, let's call it G moon. That's big G is going to be the same. Of course, it's a constant. The mass of the moon times the mass of your object over the radius of the moon squared. And notice our mass appears on both sides, so that would cancel. And so little g for the moon is big G mass of the moon, radius of the moon squared. So if I look up the numbers for that, of course this one is the same. So the mass of the moon is 7.35 times 10 to the 22 kilograms. And the radius of the moon, 1.74 times 10 to the 6. So you can see the mass of the moon is much smaller than the mass of the Earth. And the radius is, of course, smaller as well. So then when you evaluate this, you find G on the moon is 1.6 meters per second squared. And this is, it's less than G on the Earth, 9.8 meters per second squared. And this should kind of agree with our intuition, right? Think of you've seen footage from Apollo and whatnot, and you see the astronauts walking around, jumping around, bounding around on the moon. Well, that's because the force of gravity, the effective gravity at the surface of the moon, is just a fraction, maybe a fifth or a sixth of what the gravity is on the Earth. So that would explain, or it's consistent with what with what we think, or we kind of have a notion of that the gravity on the moon is less, and this is how you calculate that. Questions with that? That's an excellent question. How small would G have to be for it not to pull you back to the surface? So that gets, you can ask the question like, how small of a body, like how small would the moon have to be for you to be able to just jump off the surface? The most convenient way to analyze that is to think about it in terms of energy conservation. So we're going to talk about that later in the chapter. That's an excellent question. So that'll be something called escape velocity. We'll talk about that later. I mean, you can tell though, consider to get off the surface of the Earth, right? Like for Apollo, you had to use giant Saturn V rockets. And then they landed on the moon, and to get off of the moon, you didn't need, use just that small lunar lander. So the difference in energy required is huge. And part of that is because gravity is less. And then another part of that is the fact that there isn't any atmosphere. There's no drag on the moon. So those are really interesting questions. We'll get into a little more of that later. So let me show you one other example problem. I'll try and be, or I'm trying to be better about our time. I don't want us to, yeah, let's see here. So the other question that we want to talk about is, consider this question. I don't appear to have it in my clipboard. How far above the surface of the Earth will G be half of what it is at the surface? So let's see. So in other words, so this is sort of a related question. So let's call this G prime. So basically the situation that we have is, instead of being on the surface of the Earth, imagine how high do you have to be off the surface of the Earth so that G here, G prime, is 1/2 of G at the surface. Okay. So we would look at this in the same way. We find the force of gravity. We know that it's going to be big G, the mass of the Earth times the mass in question, over R squared. But now, this G that we're interested, we're going to call it G prime. It's only going to be half of G. So notice the mass, again, would cancel. So we're left with this expression where we're trying to find R. And let me just rewrite this. And we have the following. We have GM, mass of the Earth, over R squared is 1/2 little g. So we would want to solve this for R. So if we solve this for R, what would that look like? We'd have big G, mass of the Earth. We'd pick up a factor of 2. We would divide by little g. If we multiply this over, that would be equal to R squared. So then we would take a square root of that. And that would give us R. So, and if we put our numbers in here, so big G, 6.67 times 10 to the minus 11. The mass of the Earth, 5.98 times 10 to the 24. G, 9.8. If we evaluate that, we find that the R is 9 times 10 to the 6 meters. So this is a good opportunity to mention, so this is R. This is this whole but really we want H. So recognize that R is going to be the radius of the Earth plus H. So we can solve this for H by subtracting off the radius of the Earth. So if we subtract off the radius of the Earth here, whoops. So the radius of the Earth, recall, was 6.38 times 10 to the 6. When you subtract that, you find that this would be a height of 2.6 times 10 to the 6 meters. So this is the height that you have to be at so that G goes to 1/2 of 9.8. So that is another example of kind of the simple kinds of problems that you can solve. Basically, comparing big G and little g. And this is basically section 6.3. So, and I would mention that section has got some really cool there's some very cool examples in there. For example, they look at, what if you're on a mountain? How does G change? I think they look at, Mount Everest. Or another example they look at is, how does the fact that the Earth is rotating factor into this? So you may or may not know, I mean, all satellites and stuff are launched from places close to the equator because the effective little g, the force of gravity there, is a little bit less on account of the fact that of the rotation of the Earth. So it makes it a little bit easier to launch things. So they talk about both of those examples in detail in section 6.3. So I would encourage you to read that. Really read all of chapter 6. But next time, we're going to talk about basically connecting what we were doing before. So we're going to connect centripetal acceleration to gravity. So we're going to look at what if it is gravity that's supplying the centripetal acceleration that's allowing an object to go in an orbit. So that's where we're headed. It's kind of a neat topic, but hopefully that gives you kind of the base, the first few sections in chapter 6, and then we'll build on that next time. So, do y'all have any questions? Questions? or what questions do you have? Shoot them in the chat. So go board hours are, I mean, it's kind of arbitrary, but originally they were 9 on Monday and Thursday and 12:30 on Wednesday. But uh, I'm not gonna like watch the board because it's not used very much. So instead, just shoot me an email and we'll set up a time that we can meet. So I sent out an email about that. So yeah, basically for office hours, I will be available then, but I'm not necessarily going to be watching the board. So shoot me an email and we can meet. So yeah, here I'll put a note here regarding office hours. Email me or message me on Teams and we'll confirm a time for it. Other questions? No questions about gravity? That's okay. I mean, we'll talk more about it in the future. So I'll look into streaming issues. I don't know what the deal is. Hopefully that's not a recurring issue, but okay. Well, I'm gonna end the stream, but until next time, we'll see you in lab or in lecture on Wednesday. So have a nice afternoon, and we will see you soon.